All right, welcome back. Let's take today to just summarize all the work that we've been doing with probability into kind of this just one document to kind of just put it all in one spot. All right, so probability is the chance a selected event will occur. And when you're looking at probability, you run things called trials. So basically a trial is just when you perform an experiment. And then an outcome is the results from a trial. And then that is the data that we collect as we're kind of going through and looking at probability. If you remember, the sample space is always all of the possible outcomes of a trial. And way back at the beginning of our unit, we looked at kind of that probability number line. So we're just going to review that really quickly. So on our number line, I'm going to put 2 endpoints because probability has to always fall in between these 2 endpoints. And those 2 endpoints are 0 and 1, or 0% and 100%. So the lowest probability you can ever have is 0, the highest is 100%. Right in the middle, we have 1/2 or 50%. All right, so that kind of is that gist, and then we had those terms that kind of described the different probabilities. So if something can never happen, it is a 0% chance. We call that impossible. And then if it's it's a little bit, it could happen, but it doesn't happen very often, we call that unlikely, and that describes all that space in between 0 and 1/2. At 1/2, there's a couple different ways we can describe it. One of the ways is as likely as not, meaning it's as likely to happen as it is to not happen. Or we can also call those events equally likely. If it happens more often than 50% of the time, we say that that event is pretty likely to happen. And if it has to happen or it happens all the time, we say that that event is certain, which means nothing else could happen. All right, then we started to talk about tree diagrams. So tree diagrams, if you remember, are just a way that we can start to organize a sample space. It gives us a really clear way to kind of list out all the possible things that could happen. So we're going to draw a quick tree diagram to show the sample space of flipping a coin and rolling a number cube. In fact, you could even pause the video right now, draw out the tree, and then just check to see if yours matches mine. All right, so when we look at a tree diagram, the first thing we're doing is we're flipping a coin. So our possible outcomes are we could get heads or we could get tails. And then we're going to roll a number cube, which means once we get heads, I could get a 1, 2, 3, 4, 5, or 6 on my number cube. Or same thing with tails. Now, once this part is done, when we're counting our total number of outcomes, we're only looking at these endpoints in the branches. We don't count these parts because really this is a combination of like heads 1, heads 2, heads 3, heads 4, heads 5, heads 6. So heads 1 is one outcome. It's not heads and then 1. So all together here, if we count all this out, there's 6 with heads, 6 with tails, for a total of 12 outcomes that are possible. Now, we also talked about how the tree diagram isn't always super efficient, and unless you need to actually specifically lay out all of the possible outcomes, you might be better off using the fundamental counting principle. And this was when we multiply the number of possible outcomes in each event to find the total number of possible outcomes in a sample space. So when we look at this, This is in place of drawing out that tree diagram. So for example, I might have a spinner, and that spinner might have 4 different sections. And maybe in addition to the spinner, I'm also going to flip a coin. And in addition to that, I'm also going to roll a number cube. So the fundamental counting principle says I can count the number of possible outcomes in each event, and then I'm going to multiply them. So in our spinner, there's 4 possible outcomes times 2 possible outcomes when I flip a coin because I have heads or tails, times 6 possible outcomes when I roll a assumingly fair number cube. So now I just multiply. 4 times 2 is 8. 8 times 6 gives us a total of 48 possible outcomes. After we were done talking about sample space and fundamental counting principle, then we started to dig into what actual probability is. And for what we're doing, there's 2 basic types of probabilities that we need you to worry about. There's theoretical probability, and this is the probability of what we would expect to happen. So when we think about probability, it's like, this is what should happen. However, this isn't always the case. An example of a theoretical probability would be like the probability of rolling a 3 on a number cube. Well, in a number cube, there are 6 possible outcomes. Only one of those is 3. So our theoretical probability would be we would get a 3 on a number cube once out of every 6 rolls. The other part of probability that we'll look at is experimental probability. And this is probability based on collected data from a set of trials. So this is when things keep happening, you keep trying it out, and then eventually you're drawing conclusions from there. So for example, let's look at the situation where Hamilton is rolling a 2 on a number cube 4 out of 10 times. We want to know what is the experimental probability he gets a 2 on his next roll. So what the experiment is telling us is this is what Hamilton has done in our data. He's rolled the number cube 10 times. Out of those 10 times, 4 of them were a 2. Now in this case, we could simplify. So the probability that he gets a 2 on his next roll would be 2/5, because that's what the data is shown. We can also use experimental probability and theoretical to make predictions as to what might happen in the future. So if we go back to this same situation that we were just looking at, except for now Hamilton's going to roll the cube 60 times. We want to know how many 2s we would expect him to roll based on his experimental probability. So originally, remember, he had 4 out of 10, or 2/5. And thinking in terms of equivalent fractions, we want to know out of 60, since that's going to be the number of rolls, how many would he can expect to be 2s. In this situation, I can say, okay, to get from 10 to 60, I need to multiply by 6. And if I do that to the bottom, I also need to do that to the top, giving us a value of 24. So we would expect Hamilton to get a 6 24 times if he rolled the number cube 60 times based on his experimental data. Right. I'm going to have you pause the video, and I want you to look at this next question on your own and see if you can use what we just did to find an answer. Now, this one's a little bit different because we haven't necessarily talked about percents a lot, but if you remember, we did talk about that percents are always out of 100. So I can always make 60% 60 out of 100, and in this case, we can reduce that down to 6/10 by dividing each by 10. Now, we want to know if Fuad is making 60% of his shots from the free throw line, or the 3-point line, and he takes 15 3-pointers, how many would we expect him to make? Now, 10 doesn't necessarily go into 15 really nicely, but if you look at what we have so far here with that 6/10, we can actually simplify that fraction. So that's what I'm going to do first. So I'm going to think about getting 10 to 5 by dividing by 2, which means I'm going to take 6 divided by 2, which gives us 3/5. And now with the 3/5, I can make 5 into 15 by multiplying by 3. So we would expect Fuad to make 9 of his shots. And just one last time, just kind of reiterating, remember, probability of every anything that can happen, all possible outcomes must always add up to 1. It's never going to be more than 1. It's never going to be less than 1. And we can use that in our favor. So sometimes, and a few of you did this in one of our decimals activity, it's easier to count things that we aren't what we're looking for, more than if we're counting what we're looking for. So just an example of it adding up to 1. The probability of rolling a 1 on a number cube is 1 out of 6. But the probability of not rolling a 1 is 5 out of 6. And when you put those together, we get 6 out of 6, which is 1, which is kind of what we're showing here, that they're just always going to add up to 1. As always, reach out if you have any questions.